Okay, so my name is Per Buer. I run a small Norwegian startup called IncludeOS. So who here has heard about IncludeOS before? Wow! Oh, sorry. Wow. That usually doesn't happen. I think like first time yesterday in another talk, somebody else referred to IncludeOS, and I almost peed myself. That was really very cool. Okay, so our company, what we do is we create this operating system or this non-operating operating system. And to sort of give you a bit of a understanding of what we do and why we do it, we'll start by sort of a short history of computing. It'll be very short. So roughly the 50s, punch cards, 50s and 60s, punch cards. So systems were batch-oriented. However, they were sort of, in terms of pure efficiency, they were very, very efficient, because you would write your program onto a stack of cards. You would submit that to, and then during the night it would load, and you would have the entire computer at your disposal, and there was nothing else running on it, like nothing, absolutely nothing. There wasn't like operating systems. Yeah. However, the user experience was absolutely horrible. So if you sort of left a missing semicolon on line 5, you would figure that out the next day, because your data just weren't there and there was a compiler error instead. So then during the 70s, I saw this picture at least once on yesterday. So this is the DEC PDP-11, was the system where Unix was born. And of course, these things were, computers at that time were quite expensive. So I think like the DEC was about $100,000, sort of if you got it with a reasonable set of peripherals. And you had to share it. And in order to share it, that was a sort of a new concept at the time. It was sort of first attempt at sort of virtualization, except the sort of virtualization, it wasn't what we think of as virtualization today, but they created a virtual system which was your sort of shell and your process space, and that was your virtual computer. Of course, today, what we require for a virtual computer is that virtual computer is more or less identical to a physical computer. But sort of this virtual computer interface. So computers went from being single process to being multi-user and multi-process. And of course, the overhead of this was really horrible. I think like up to 20% of the cycles were lost, and we ended up at the end of the 70s with basically this design, where we have user space and a kernel space. In the kernel, we talk to hardware, we police users and processes, applications running in user space. So on Intel, that's ring 3 and ring 0 in the middle. And then we have that barrier there that's supposed to sort of secure it. It turns out it's a bit porous. And it also completely kills performance. So previously I worked on, for almost 10 years, I worked on a project called Varnish Cache. And sort of one of the sort of absolute rules of stuff developers couldn't do is talk to the operating system, unless you really, really have to. Because like we were sort of handling an incoming connections, and they were typically coming at speeds of 10 to 20 to 30,000 per second. And if you sort of talk to the operating system to get some memory, things might queue up and you'll be dead. So, but that design there, like how relevant is it really? Because like most systems aren't multi-user systems anymore. Like the systems we deploy in Amazon, like how many of them have more than one user? Like, I don't know, maybe 1% or something? I think it's rather quite few of them. Because we sort of moved completely, moved away from using those facilities in the operating system. Like most people today, they write an application and they deploy it on a fresh set of virtual machines. Like unlike the 90s, where we had the server, and I would write a little silly web app or something, and then it would be deployed on the server. Yeah. Of course, this thing is likely not multi-user and multi-process as well. Yet we still use a multi-user and multi-process operating system. So now let's get to IncludeOS. So what exactly is it? So basically it's a library. Like most of the functionality is in libraries, and those are sort of provide different Ethernet drivers. There's some firewall code, memory management, IP stack, etc. And the idea is that when we build your application, what we do is inject parts of those libraries into your application. So basically we look for system calls, and instead of system calls, we inject library calls and the supporting library. So whenever the operating system, whenever your application was supposed to do a system call, it will do a, then we slap a bootloader on it and off we go. So this is typically what sort of how on your application typically what it looks like when it's linked on Linux. It has some application specific libraries which links against generic libraries which against the kernel. Unlike our systems where we have like a bootloader, there's some, it's all in a single binary, single ELF binary. Yeah. Yes, so there are a few things that are sort of, so we refer to these systems as unikernels. I would say that we are sort of try to be the pragmatic unikernel. So we sort of, from an engineering background, the code is written in C++. We are happy to support multi-core systems. We're not really that opinionated about what you do on top. And we are perfectly fine with running on bare metal. Which I think like most of it is because IncludeOS was written after sort of para-virtualization wasn't a thing anymore. And we have gone back to sort of full virtualization again, which basically means that it wasn't really that much of an effort to move to booting on physical hardware. Okay, let me see if I can try to demo this then. Because like that's like what I really would like to see happen is that you sort of go away here without being afraid of the system itself. So I stay out of the editor wars. So via Emacs, I use cat. It has quite sophisticated line editing, and it's definitely underrated as an editor. So you see now where the project has its name.
I'm disappointed you're not binary editing.
Yeah. This 90-degree angle with the keyboard isn't really okay.
The current volume is 100%.
Thank you. Yeah, well, I don't need to explain that. I think most of you know enough C to. So boot is the command we grabbed to sort of boot up an instance. There's nothing else called boot as far as we know, so we just sort of grabbed that. It needs super user privileges in order to set up networking. So If it wasn't for that, it wouldn't. Yeah. So basically, just it built an operating system, sort of perhaps the world's simplest operating system, the Hello World operating system, and booted it up in a VM, and it says Hello World, and then sort of halted. So, like with stuff we made, I think we succeeded in making the simple stuff simple. I think that what Bjarne said was make the hard stuff possible. Okay, so I will now come to the first party trick that we have, something called live update. So this came out of the need to sort of continuously develop software, and you sort of deploy, and it's a pain in the ass to do that because you're running a VM, you need to shut down the VM, replace the binary image, and then boot it back up again. So since basically what's running inside a VM is basically just a sort of stream of bytes, sort of that's a gigabyte of bytes, we can sort of we can basically replace stuff that's happening there. Sorry. So this is a virtual machine. That's the current sort of application that's running there. So it's a map of the memory. Whenever it boots up, it has the option to connect to a master node, a management node. So it boots up, it establishes the node to the master. The master can then sort of push down an image, an updated image, through that connection. So now have the situation where we have a virtual machine, we have two basically copies of the application, except one is updated and one is not. Basically what we can do then is we can basically just store the state of the current operation, of the current running application. And like serializing state is quite a common thing to do now. Just store it at a very sort of specific state. And then what we do is just actually just boot the new kernel, and then we restore the state, and then we sort of discard the old stuff. And discard this as well. And what has happened now is during about 100 milliseconds, we have replaced 100% of the running code with completely new code, and there's nothing left of the old code. So it doesn't necessarily just limit itself to updating. We can completely change what's inside of that sort of VM. We actually use this when, so we have a sort of commercial product where we do firewalls and load balancers. And what we actually do, the way that works is that we boot up these blank VMs that have no functionality except this live update functionality. And then whenever the sort of customer decides they want that a firewall with this specific firewall set, they just push it out through this mechanism. Yeah, so this is the, let's do another demo. I think this will be tricky because, yeah. It's not the brightest application. Oh, no, well, that worked out quite well, I think. Okay, so let's see. So what I boot up here is an IRC server. And we can then Why did this work? Let's see. Oh, it's the wrong port. Yeah, it is. But it was. Oh Oh, he said connection refused. Yeah, of course. There we are. Yeah, well, it's a bit. There's this ASCII. Yeah, you can perhaps tell that it says IncludeOS or something here. Okay, excellent. It works. So this is now sort of a running IRC server and a running IRC connection to it. Great. This thing here, the message of the day, is actually sort of hard-coded. It's compiled into the application itself. What we'll do is we'll just. No, it's called. Yeah.
Who would you like to call?
Okay. I'm probably pressing buttons. Yeah. Okay. Hello. Take down. And then we. What I do now is I rebuild the project and create a new binary, and then I have a completely new binary of that system, and then we have an update script, which is basically just, yeah, it does the build on everything, so I didn't have to do that. Yes, the server sends out a server notice when it's updated. And oh, of course, I used too much time and it idly closed down the connection. But you did perhaps notice that the TCP connection did actually survive the update. So we did actually manage then to sort of retain a TCP connection and sort of still replace all of the running code. Yeah, I should have done this a bit faster and would have been a better demo. So that's our party trick. Any questions so far? By the way, we have quite ample of time, so feel free to interrupt me if you have any questions or comment. There's also sort of, so concurrency is also sort of a sort of topic that's opinionated within the sort of unikernel community. Most people think that the unikernel should only have like a single core and should only run sort of non-threaded event-based applications. As I said, we're not really of that opinion. So what will since also one of our targets is sort of bare metal hardware, just being able to just run on one core would be just silly. So the way that we used to have multi-core SMP support, and then this year we sort of broken it, and we decided to sort of leave it out until we fixed some other stuff because there's not really that much demand for it. But the idea, rough idea, is this: that you have a four CPU system. It'll sort of boot up, and like IncludeOS has an event loop. So that's what we'll do whenever we boot it up, is sort of to stay in that event loop. And basically what happens on sort of SMP systems is that they all basically run this event loop. And then you have this add task function where you can basically just take a function call and direct it at a specific CPU, and it will run on that. And I'm sure sort of we'll at some point create abstractions on top of that. And I think like Alfred sort of been planning to sort of get POSIX-like threads and have being able to create POSIX-like threads on top of that, with of course the limitation that we cannot have more threads than we have CPUs, because like process preemption is currently sort of not on the roadmap. it's not that it's sort of magic or anything. It's just sort of vastly inefficient, and I think like Alfred is doesn't like that. Okay, a bit about developing with IncludeOS and what it sort of offers to developers. So as I mentioned, the native interfaces are all event-driven. That also means that I mean, with C you have the sort of standard POSIX interfaces that you can sort of use. If you want to do stuff event-driven in C++, you basically have no standards. As far as I know, it's not really standard. So the networking APIs are sort of proprietary to IncludeOS. Yeah, there's no scheduling. There's multi-core support. The big project we've been working on I would say probably most of the year has been replacing the C library. So we used to run a little library called newlib, which I think is very popular in embedded amongst embedded people. It's a very minimalistic C library. So it doesn't really offer much except what it has to. Muscle is a sort of interesting project because what it does is, in addition to offering a standard C library, it also offers POSIX, which is quite rich on top of the C library. We've tried implementing parts of POSIX previously when we had newlib. It's a soul-sucking experience to implement. I have no idea why the people who did write Muscle actually implemented all of POSIX on top of it. I'm very impressed that they did. But the nice thing is that we can now unlock parts of POSIX as long as we can provide the underlying system call-like functionality that Muscle expects. Muscle is actually sort of written explicitly with Linux in mind. So another operating system coming cheekily along and taking it and using it wasn't probably planned. But what Muscle expects is just for there to be sort of Linux-like system calls beneath it. And if we can provide those, it will sort of unlock the relevant parts of POSIX. So this means that we should at least have enough POSIX that you can run all of the libraries that you like. It'll be yet some time before we can say that the same thing about applications. Applications do things like forking and stuff like that, which doesn't necessarily make sense on IncludeOS, but at least the applications should be available. Yes, debugging also sort of slightly different. It's more akin to embedded. I mean, we do cross-compile when we compile an application. So that means that you might want to sort of bring your own debugging stuff into your application. I mean, there are developers that work with us that do sort of printf style debugging. That's their favorite thing to do. You can actually attach GDB to a sort of running VM that runs IncludeOS, and then you can sort of single step and set breakpoints. Another thing that we also have a Linux compile target, where we would basically just run inside a Linux process, and instead of a PCI device for networking, we just get packets in and out of the tap device. So I think like that's probably likely the easiest way to sort of, because then you have basically very few limitations on what sort of tools you can use. Okay, so yes.
You mentioned about the add task.
Yes.
Cores.
Yes.
Is the memory a uniform address space across all cores, across all tasks?
Yes.
So any task can access memory from any other task?
Yes, there's only one address space.
So that's not virtualized in the slightest or sectioned or segmented?
It is virtualized. I mean, there's paging Yeah, but it's all. But it's all. There's only one. It's only one address space. Yes.
So I can pass a pointer from one task to another, dereference it back.
Yes.
Thank you.
Oh, I should have probably repeated the question. Yeah. It was like, do all the CPUs see all the same stuff? Can you pass references back and forth and pointers? Yes, you can. Yeah, there's also we have actually discussed, by the way, having like several address spaces. So one of the things that sort of we could potentially do, which is actually could be quite cool, is so it's running in ring 0, because like and some people find that scary because you can sort of modify the page tables when you run there. I don't really think it's scary because like if that gets compromised, everything will get compromised anyway. So it doesn't really matter, and you're still trapped inside the VM. So I don't. But there is an opportunity to actually boot up in ring 0, and then boot another unikernel in ring 3, which then doesn't have that opportunity to modify its own page tables. That of course would wreak havoc on sort of live update, and we need to rewrite quite a bit. But then, if that gets compromised, it wouldn't even be able to alter the page tables. Yeah. Okay, so what can this be used for? Network functions. So these are, so back in the day you used to have physical switches and load balancers and firewalls. Today data centers are mostly virtualized. They run vSphere or something like that, OpenStack, some sort of thing. And of course the networking functions are virtualized as well. So the first thing we actually did as a sort of commercial company when trying to build something was look at sort of load balancing and firewalls. We're going to try to do that. A firewall is, after all, just a router. We already had the router. And firewall, the firewall's default policy is just not route packet, and the router's policy is route packet. So like, how hard could that be? So we started off by sort of, if you look at sort of the way traditional firewalls are built, this is, they do have like these firewall rules. They're basically just a linked list of rules. And as a packet comes in, it gets basically shoved through that list. And if it matches, something happens. We accept it or reject it. Now, when we sort of started working with this, how do we, this means we have to have some sort of configuration file or something that we have to sort of load and then reload it. And there was, and it didn't really sort of, there was something wrong with it. So what we did, and I've proposed this for a talk next year, because I think it's a really cool use case or cool design. So we created this super simple domain-specific language where we, so allowed ports. That's basically a list of these ports. This is a list of hosts. We can have a list of everything. And then the first firewall rule, if IP source address is in nice host, then, and if the TCP destination port is in allowed destination port, we accept the packet. Like, it's super simple. It's actually, for those of you that dealt with IPtables rules, it's actually a lot more pleasant to read this stuff than to read IPtables rules. So what we actually do is we compile, transpile this to C++, and then we link it into the binary, and the packets basically run native code as they sort of traverse the rules. So for us, this is actually simpler to handle than, I would say, probably a traditional configuration file. But one of the things, it's also a lot more friendly towards the CPU. So, yes. So Oslo Metropolitan University, there was a master's student there who did a comparative analysis. So this is Linux. These are the number of firewall rules, and this is the throughput measured in gigabits. So out of the gate, we do like 10-12% faster. We're 10-12% faster than Linux already. But as the number of rules increase, Linux has to shove that single packet through that enormously long list, and it sort of slows down. And I think like you can see sort of where that list starts to wreak havoc on the CPU cache. It's I think it's like here. The entire list doesn't fit anymore, and things go really downhill from there. Whereas we're still at that, we basically don't notice that we have to process these 5,000 rules. Yeah. Yeah, there's a quick note on eBPF and NFtables. I think IPtables will be dragged behind the barn and shot at some point in the near future and replaced with better stuff. NFtables and eBPF are two of the proposed solutions to it. But I do have to say that I think like the firewall was built in a matter of 2-3 months. And these projects are at least 10 or 20 times more complex. And we offer I would say probably a better performance. Yes. So that's what we've been doing today. What we'll likely do in the future is CPU-based IoT. So, I mean, IoT, you can roughly divide it into microcontrollers and CPU stuff. Microcontrollers, I think like all the people I talk to, they seem to be reasonably happy. They have a choice of relevant operating system to choose from, and they work reasonably well. For CPUs, there's basically Linux and QNX, and they're not really that happy about those choices. Basically because of a core feature of Unix, which is the ability to reconfigure the system. So this made a lot of sense for all Unix systems that are servers or desktops or mobile phones or even TVs, that you can the user can reconfigure the running system. However, in my opinion, it does not make any sense at all for devices. So at home I have a Wi-Fi router. It runs Linux. An attacker, if he finds a flaw in that piece of software, which leads to remote code execution, he could actually reconfigure that system to do something else. So it could like sniff packets or mine bitcoins or do spam bot or do something else, which I don't really see the need for that. I think like 99% of the people buying Wi-Fi access points, they don't want that device to change functionality, or at least they don't want any user to be able to add functionality to that system. Of course, the vendor decides that it should have more functionality, then, and I think there's a similar situation for a lot of CPU-based IoT devices. Linux is, I would say, probably in very few situations the right choice, basically because of that reconfigurability. So that's wrong with the my gripe with the general purpose operating system. This summer we have some awesome news. We got a significant chunk of money from the European Union, from the Horizon 2020 program, to actually port IncludeOS to ARM and to at least get a couple of boards up and running with IncludeOS. So hopefully, maybe in around a year, we might be looking at booting on ARM stuff. But likely 64-bit Cortex-A. Okay, ultra low latency. So there, if there's no operating system, there's nothing that can get in the way, or it's very explicit what could be in the way. So when an interrupt fires, we can actually respond to it quite quickly. Actually, over beers yesterday, we discussed the situation of maybe we should just turn off interrupts and maybe just busy wait when we have nothing else to do. Like because why not? Because there's nothing else on that system, so we might as well busy wait. Which means that the moment there's a packet, we can process it right away. So I was on a talk where high-frequency trading was discussed, and it's been interesting to hear how much effort is being put into sort of disabling Linux, because that's basically a lot of what these people do. They try to disable Linux because they don't use the networking stack. They bring their own into the application. They don't, maybe not even using the I/O stack. You have user space disk drivers. They sort of disable completely or try to disable as much of scheduling as possible because they don't want anything else. They try to disable as much of the CPU cache as possible, trying to pin pages in the cache, etc. Which is this sort of, but if you don't have, if you have a non-operating system operating system, all of that is already done because we never sort of implemented those features anyway. Yeah, so we have a really good latency response, and it'll be interesting. Function as a service has been sort of mentioned as a case. I think like that's, for me, it's mostly an academic exercise. Since I don't own Amazon, I can't really sort of create a function as a service platform because nobody will likely use it, because like just a function as a service platform doesn't really bring that much value unless you have all the other services around it. There's a good example of this current industry problem where unless your Amazon, Google or Microsoft, infrastructure innovation doesn't really likely happen. A lot of it, yeah. General purpose APIs. We can use this for IRC servers, or there's a web-based a web toolkit that we have also created. Yeah, we'll see if that sort of catches on. It sort of, for that to happen, you have to actually want to write your APIs in C++, and people don't seem to do that. Anyone here does that? Like web API in C++? Yeah. So what's happening in the future? ARM64 support. The reason we say ARM64 is just because the muscle library was written first. They wrote likely the 32-bit version, and then they wrote the 64-bit version, and the 32-bit version is hard for us to sort of plug into our build system because it was not as elegantly designed. Bare metal support will likely improve. So there's stuff we need to add. So currently we have 3 Ethernet drivers. One of them is available as a physical card, which is the E1000 driver. We'll likely either look at Solarflare or Mellanox and see if we can add support for one of those 2 cards, so we can try to sort of play with ultra low latency applications. Yeah, we should likely at some point add more hypervisor support. So currently we run on Linux and VMware. So Linux is KVM basically. So that is most of the market. The new Amazon instances we can run on them. What we don't run on is Xen and Hyper-V. Yeah. So if anyone really wants to see us on Hyper-V, come and see me, and we can talk about it. Yeah. Yeah, I think that is it. None of us know anything about ARM. And we just got a shit ton of money from the EU to port our software to ARM. So if anyone here would like to spend a couple of years porting a brand new operating system to ARM, I would be very happy if you can come and see me. Yes, yeah, I think the recurring theme from Alfred's talk yesterday was we have no idea what we're doing. Which is okay, any questions? No questions, really? Yeah? Yes?
You mentioned latency support for low latency support. Do you have any figures comparing a simple, with an operating system with IncludeOS?
Yeah, so the question was, do we have any figures for ultra-low latency applications? And so there's because of the goddamn interrupt controller on the computer in the office, we haven't got networking to work on bare metal yet, because there's a MSI-X controller, which is the fancy way of routing interrupts, and we don't support that yet, unfortunately. But what we have done is run the stream benchmarks, which are these really combination of computation and memory bandwidth benchmarks. What we saw was that on average, like Linux would run one benchmark in 33 cycles. And not entirely sure why, but we would run them in 32.7, which is 0.3 cycles better. There's some noise that is typically introduced by sort of various hardware inside the computer. We do run like a % faster than Linux on pure memory-based workloads, which I think is quite cool. Yet to see how the event model handles external interrupts. Yes. Any other? Yes. So the question was about user interfaces and graphics on bare metal. We do have support for SVGA frame buffers. So I think like there was this guy who sort of ported some retro games to IncludeOS. So those work. I guess that's not really what you're interested in. I know that there have been some people in the Qt community that have looked at IncludeOS for basically embedded devices with screens that could look at running Qt. That's all I know. That there have been interest there. Is Qt what you're after? Yeah, I thought so. Any other questions?
If I'm familiar in line with existing C++ code, how easy is it to get it to run on any device?
Yeah, so this is an existing application or an existing library? Yeah, Alfred?
Well, first of all, we do have features. You don't need it? Okay. I mean, we have Linux has 318 system calls or something, and we implemented 42 of those. Huh? Yeah, I mean, most of the, I think at least in my mind, the only really hard or features that are left that are relevant would be clone. So we have some, we don't have a workable hack for clone, but we make something really good spreading, and it's going to take the rest of the year probably. And usually that's been the most, when we try to force stuff, that's been hands down the first thing that's been troublesome, is that there's so much. So if you don't have that, I mean, you can import OpenSSL. So we have that. And you can actually link in already pre-compiled OpenSSL from the Ubuntu. So actually that was the first thing we did, was take the Ubuntu step to compile OpenSSL.
Yeah.
So that worked. Tried to, for example, send the UDP packet in the beginning. We do have the basics of sockets, of POSIX sockets, but it's kind of portable, no motivation for us to put this whole socket layer on top of our own basic API, but we have like the basics. It's hard to say. I don't use it as short.
Yeah.
What compiler do you use?
So the question was what compiler
And I'd
we
like
use.
to know the full version.
Yeah, Clang 5 or 501, I think, like that was the. Yeah, 608 as well. Okay. Yeah. Yeah.
So it's not too painful.
It's not too painful. Yeah.
And your build system is CMake.
It creates slow code, but it's predictably slow code. It's not as fast as GCC 6 now.
Don't worry, GCC GC now is as slow as Clang, so that's okay.
Okay. Yeah. If we build with GCC, it builds nicely, just doesn't boot. Yeah.
The problem is that we have a dependency on libc++. So we build our own libc++. That has to be built for our muscle. First has to build muscle for IncludeOS. Because we slightly changed how the syscalls actually look. And then you have to build libc++ for that. And then if you try to build the application with GCC, you're reaching a libc++, then you have some problem. But in principle, I think.
Yeah. So I think we're at the point in time where we should end. So thank you very much. If you have any questions, please grab me, Alfred.